Hello students, this video is about polynomial functions, and in it we're going to be talking about in behavior and analyzing the graphs of these polynomials and also just identifying the maxima and minima points. So first of all, in behavior. In behavior is a description of the values of the function as x approaches infinity. So what happens to the function the further and further you go out the x-axis, either approaching infinity or approaching negative infinity? The degree and the leading coefficient of a polynomial function determine its in behavior. It is helpful to know this when you're graphing a polynomial, what the in behavior will be. So the degree and the leading coefficient are what tell you the in behavior. The exponent of the first term, when written in standard form, is the degree of the polynomial. So a polynomial is in standard form when its terms are written in descending order by degree. So, okay, and the leading coefficient is the coefficient of the first term. So here's a polynomial, and you can see that it's in standard form because the degrees are in order. Here we have degree 3, and this next term has a degree of 2, and the next term has a degree of 1, and then 0. So they're in descending order. And the highest degree is 3, so that's the degree of the entire polynomial. And then the leading coefficient is the number in front of that, and in this case it's 5. We have a positive 5 for the leading coefficient. So when we look at that leading coefficient, if the leading coefficient is a positive number, a is greater than 0, then that tells us about the in behavior, that the function was going to end going up. See how this one, if you look at the arrow to the right here, this arrow is going up. So that means that as x approaches infinity, which means as we go further and further out the x-axis this way, the function itself goes up higher and higher and higher. So what happens to the function, to the red line, the further we go out the x-axis? And since a is greater than 0, it ends going up. And here, this one, look at the arrow on the right side, it ends also going up. So even though this one started down, it ends coming up. It ends coming up. That's how the a is greater than 0. And if the a is less than 0, then as x approaches down here, as x approaches positive infinity, which means we're coming out this way, out positive infinity, the function, the polynomial in terms of x, approaches negative infinity. So the polynomial, the red line here, is going down towards negative infinity. And that's because the a value is less than 0. So if the leading coefficient is less than 0, then we end going down. And notice how this one ends going down. And then we have an odd degree versus even degree. Odd degree means that the arrows are going to face different ways. Here, one arrow starts down and the other arrow ends up. And here, the function starts high and then ends low. So the odd degree are opposite ways, whereas even degree, both arrows go up or both arrows go down. So let's say that one more time. If a is positive, then the last arrow ends up. So the arrow on the right goes up. And here, the arrow on the right goes up. If a is negative, then the arrow ends down. So here, it ends to the right, it comes down, and to the right, it comes down. If the degree is even, both arrows end the same way. So here, both arrows go up, it's even. Both arrows go down, it's even. If it's odd, one is up and the other is down. So here we have one going up and one going down, or here, one going up and one going down. So let's look at an example. Okay, wait, the graphs of polynomial functions are classified by the degree of the polynomial. So here we have polynomials of different degrees. 0, we have a linear with a 1. Quadratic, you guys are familiar with. The highest degree here is 2, okay? Each graph, based on the degree, has a distinctive shape and characteristics. So we know that linear makes a line. Quadratic, we have a parabola. Notice with the degree of 2, okay, let me just go back. Notice with the degree of 1, how many directions does this graph move? It only moves one direction, it goes up, 1. Whereas quadratic, the graph moves in 2 directions, degree of 2. It comes down, 1, 2, turns and comes back up. So it has 2 different parts here going in 2 different directions. How many directions does the cubic go in? It has a degree of 3. Watch. 1, 2, 3. So you can count, you kind of see what the degrees would be based on the shape of the graph. Quartic function 4. 1, 2, 3, 4. So that's kind of interesting and fun. You can know what the shape of the graph is going to look like by the degree of that polynomial. Here's 1, 2, 3, 4, 5. Okay, so let's see if we can identify the leading coefficient, degree, and end behavior. Here we have a leading coefficient of -1. Okay, so the leading coefficient is negative. That lets us know if the function is going to end facing down. Then we have a degree of 4. Okay, the degree of 4. 4 is even, so that lets us know that the function is going to end and start. Both arrows are going to face the same way. So if I were to make a little sketch of this, it might look like this. 1, 2, 3, 4, and both arrows pointing down. Now look at this and let's see what the end behavior would be. Here we can see as x is going this way, as x is moving in the positive direction, the function is going negative. So as x approaches negative infinity, the function p of x approaches negative infinity. So as x is going to negative infinity this way, on this side, the function is going down. And as x approaches positive infinity, so as x is going on this side, okay, the function is also going to negative infinity, going down. Okay, the next one has a leading coefficient of 2, and the leading coefficient of 2 is positive, so that lets me know that the function is going to end facing up. So instead of an arrow going down to the right, the arrow is going to go up because it's positive. The degree of the polynomial is 5, so that means that one arrow is going to face up and one arrow is going to face down. So since we know it ends facing up, to start we're going to start facing down, so it's going to look something like this. Starting going down, and then 1, 2, 3, 4, and ending going up. Okay, so, and I didn't actually graph it. I mean, you don't have to actually, just sketching out what curves are in there. So now, what is the end behavior? As x goes to negative infinity on this side, what happens to the function? On this side, x is towards negative infinity. The function is headed down. The function is also approaching negative infinity. So as x approaches negative infinity, the function approaches negative infinity. As x goes up to positive infinity this way, the function also goes up. So, do you think this function is odd or even, and does it have a positive or negative leading coefficient? Well, when I look at this, I see one arrow going up and one arrow going down. That lets me know that this must be an odd function. An odd function. Here it is. Has an odd degree. Now I can actually count and see what that degree must be. 1, 2, 3, 4, 5. So it changes directions 5 times, so I would guess the degree would be 5. Now, how does it end? It ends going down. Since it ends going down, that means that the leading coefficient must be negative. Okay, and we can describe the end behavior by saying as x goes out to the let's do negative first. As x comes out to the negative side, the function itself is increasing towards positive infinity. As x approaches negative infinity, the function approaches positive infinity. And as x approaches positive infinity on this side, the function approaches negative infinity, going down. How about this one? Okay, so I see that both arrows are going up, so that's going to mean even. And I would say 1, 2, 3, 4, okay? And then let's see. Odd or even, positive. Okay, so then the arrows are facing up. Okay, so facing up means it's going to have a positive leading coefficient. And then we can talk about the end behavior. As x is going to the negative side, the function goes positive. And as x is also going to the positive side, the function also is positive. Okay, so I also want you to be able to graph these. When we're graphing them, there's a couple of key attributes we can find, pretty much using our calculators right now, although it's possible to do these things without it. You can find the real zeros, the y-intercepts. You can... Okay, so let's go ahead and graph these on our calculator and see if we can describe the graph and identify the number of zeros from the graph. So we're just going to put this directly into your calculator, and then after you do that, you might have to change your window so that you can see it clearly. Just a basic window from -10 to 10 would probably work. Looks like this one maybe is from -5 to 5 on the x values. You can see that the graph crosses the x-axis 3 times, crosses here, here, and here. So it looks like there's going to be 3 zeros then for the function. From left to right, the graph increases, then decreases, and increases again. It crosses the x-axis 3 times, so there are 3 zeros. And here, when we put this one in the calculator, we can see that it appears to have 1, 2, 3, 4 zeros, 4 places where it crosses the x-axis. And this graph increases, decreases, increases, and ends decreasing again. So we can see, because it has a 4 degree, that it's going to be both of them end up going the same way, and they're both going down. And then because we have a negative, it ends going down. So, okay, next is a critical point, a turning point for the graph, where it changes from increasing to decreasing. Whenever that happens, we have a local minimum or maximum. And the local minimum and maximum are minima or maxima. Okay, and let's see if we can find those. We can actually do this on our calculators. We can go ahead and graph it on the calculator. And from the graph, it has one maximum up here when it goes from increasing to decreasing, and then one minimum over here where the graph goes from decreasing to increasing. So we're going to use the second calc button above the trace to find the maximum point. You're going to push second calc, and then you have to guess a value to the left of it and a value to the right of it, and then your calculator will estimate in between where that maximum is, and we get the maximum to be at 21.8. And then we can also find the minimum using the same method, second trace, and the minimum is number 3, and we get -19 for the minimum. Okay, an artist plans to construct an open box from a 15-inch by 20-inch sheet of metal by cutting the squares from the corners and folding up the sides. Find the maximum volume for the box and the corresponding dimensions. So the first thing you have to know to do that is that volume is length times width times height. So we can find, so let's just let one of the sides of the box be x, the length, I guess, and then the width, we would have to, we know that the width of the piece is 15, we would have to subtract 2 of those x's from that, and then the other side, the length is 20, we'd have to subtract 2x from 20 as well. So this is an expression for length times width times height. Now if we graph that, we can look at it and see where's the maximum volume. So when we graph it, we can find the maximum using that second calc again, and the graph has a local maximum of 379.04 when x is 2.3. So the largest box will have a dimensions of 2.83 inches, and then 15 minus that and 20 minus that for that total volume. So great. We've learned these things, and this video is done.